In this video, we're going to see varactor diode. Varactor is a short form of a variable reactor. Var comes from the first term and actor comes from the second term. And it is also commonly known as varicap diode, which is again a short form of variable capacitor. Var comes from the first term and cap comes from the second term. Conventional PN junction diode has capacitance property which changes with respect to potential applied across the PN junction diode. But then varactor diode is specially designed to exploit the voltage variable property of the junction capacitance. When we say junction capacitance, it's actually the transition capacitance of the PN junction. Usually a varactor diode would be one side highly doped and the other side the doping would be specifically tailored and modified to meet the application requirement. So to start with, let me take P side is highly doped and N side is lightly doped so that the depletion width would extend primarily into N side. Based on our doping profile assumption, I have plotted Nd minus Na here, where I'm assuming this side is P side, which is highly doped, so P plus, where Nd is 0 and Na is a high value, so I've represented in negative direction. These lines indicate that there is a lot of range in the middle, which indicates that the doping that we have done is high. And this side is N, and the doping is like this. This looks exactly like what we have discussed previously. And if the doping profile is like this, we can say it is actually abrupt junction because the doping concentration is changing abruptly at the metallurgical junction. Then we can say the junction capacitance, which is actually the transition capacitance, CT. Now onwards, we can say CT is also called as CJ, the junction capacitance. So CT we know is epsilon A over the depletion width. And we know the formula for depletion width in abrupt junction case, which is given by this formula, where VR is the reverse bias voltage applied across the PN junction. Once doping is fixed, we know this term is a constant, and for a given semiconductor PN junction, these terms would be constant as well. So we can write the depletion width W is equal to constant K times VBI plus VR whole power half. And of course, for a given doping, VBI will also be a fixed value. But now let me write W would be directly proportional to VBI plus VR whole power half. And in case if we assume VR is far greater than VBI, we can simply write this as W is directly proportional to VR power half. We can rewrite the junction capacitance if we know the cross-sectional area of the diode. And of course, epsilon would be fixed if the semiconductor material is known. And we know W, which is directly proportional to VR power half. So we can write the junction capacitance as directly proportional to 1 over a VR power half. So we can rewrite this as a VR power minus half. And this is for abrupt doping case. Now there are different kinds of dopings that we can actually do. And let us see one kind of doping which is called linear doping, which means on N side, I'm going to assume the doping is going to be linearly increasing as we increase the distance x, like this, where we call this linear graded junction. And of course, we didn't derive the transition capacitance for this kind of doping profile. At this scope of the course, we are not going to derive it, but still we'll use the formula directly, where CT would be directly proportional to VR power minus 1 over 3. And there is another doping profile which is called as hyperabrupt doping, and the junction is called hyperabrupt junction. And the profile would look like this. And this would be called as hyperabrupt. So to understand this, if you see, for the first case abrupt, basically the doping profile was suddenly changing to another constant value. In linear case, it was changing, but it was linearly increasing. Whereas in case of hyperabrupt, it increases to a too high value and suddenly drops down. So we call at the junction, it is hyperabruptly changing. So we call this hyperabrupt junction. It seems for hyperabrupt case, the junction capacitance would be directly proportional to VR power minus 2. And in all our three cases, we have kept the P plus side doping same, Whereas here, the doping in all three cases has been changing. To represent this in a very generic way, let me write the doping on n side is some constant g times x power m. For abrupt case, m value would be 0 because the doping concentration is not changing with respect to x. So let me write m is equal to 0 for abrupt case. And for linear doping, m would be equal to 1 because it is linearly increasing with respect to x. And in hyperabrupt junction, it would be minus 3 over 2. And now, in a very generic way, if you want to write the depletion capacitance, Ct can be written as Vr power minus n. And now we can find a relationship between m and n. It so seems that n is actually given by 1 over m plus 2. And let us make a list of them. In linear case, where m is 1, n would be equal to 1 over 3. And when m is 0, in case of abrupt, the value of n would be half. And in hyperabrupt junction, where m is minus 3 over 2, n is equal to 2. As we see, m is decreasing and n is increasing. And we can see as m is decreasing, n is increasing. And you can observe here that we are changing doping profiles in such a way to actually impact how the junction capacitance changes when we change the reverse voltage. So we are basically tailoring the doping in such a way that we get a better characteristics or better control of the junction capacitance by varying the reverse bias potential. To understand this better, let me take some graphs. I'm taking 3 different plots for 3 different diodes. Let's say this is for conventional PN junction diode, and these are specific to, let's say, varactor. Cmax to Cmin ratio of a varactor diode is very important to look at. For a conventional diode, the variation of capacitance within the given voltage variation would be small. For a varactor diode, the variation of capacitance would be higher because we have particularly tailored the doping profile in the PN junction diode. That's why it is very different from a conventional diode in terms of Cmax to Cmin ratio, where Cmax to Cmin ratio would be higher in varactor diode and less in conventional diode. And a typical value of Cmax to Cmin for a varactor diode would be around 5. For a linear graded junction, the capacitance variation would be higher at low voltage of operation, whereas for hyperabrupt junctions, the capacitance variation would be higher at higher voltage of operation. This is all with respect to the conventional PN junction diode. Varactor diode symbol would be like this, just like a PN junction diode, except that we represent the capacitor explicitly in the symbol, where this is anode, this is cathode. If you look at applications, varactor diode is basically a variable capacitor. Now you can think about wherever you want a parameter called capacitance to be varied to achieve some characteristics, we would be using there. For example, voltage controlled oscillator, where the frequency can be controlled with the voltage applied, because the frequency depends on capacitance parameter, and if you can change capacitance, frequency changes. Tuned circuits especially, to tune into a particular frequency or channel to receive the signals, we'll be using this varactor diode to change the center frequency of the receiver filter. Parametric circuits. Let's say an example for parametric circuit is you have a filter which is designed with a capacitor, and you don't want to remove the component as such, but still would like to change the characteristics of the entire filter. Then if you have varactor diode, just based on the voltage applied across the varactor diode, you can change the capacitance. As a result, the bandwidth, the center frequency, and stuff can be changed. And similarly, you can think about parametric amplifiers and stuff like that.